realise that R has got a built-in way of doing it. So I'll show you how to do it now. There's my data. qqnorm does that for us. Our function qqnorm does this for us. If x is Gaussian, qqnorm x gives a straight line. Perfect straight line? Of course not. Can't be a perfect straight line because we've got random variability. There's crud everywhere. But it ain't too bad. You can see it's turned it into the theoretical quantiles and it's kind of transformed the x-axis. But the y-axis is showing us where the data lies. And it's not a perfectly straight line because it's random. I can make it more straight. Let's put a few more zeros here and see what happens. 2000, there we go. That's nice and straight, isn't it? Where's the scruff? Right at the extremes of the distribution. The distribution, any distribution, has got more uncertainty right at the ends of its distribution than the beginning. So we can see that it looks straight apart from the edge there, apart from the very end distributions. But as the data gets more and more sparse, as we just get a smaller and smaller data set, we see bigger and bigger deviations from a straight line. I'll show you what happens if the data is not Gaussian. You'll remember shape 1 and shape 2 from the beta distribution. That beautiful straight line has been lost and we see a curve on our data. Okay? The transformation that qqnorm uses is specific to Gaussian. That's one of the beauties of the Gaussian distribution, that there exists a nice transformation in order to make the line straight. Not a lot of distributions have that. And of course, the more severe the distortion is, well, let's try chi-squared. We've got a curve that looks like that. Go back to Gaussian. Snaps into focus. You can see that beautiful straight line. Here, of course, the mean is 0 because the default value is 0. But what I can do is just put the mean equal to 3, and it should be obvious what's going to happen to the plot. It's going to just take this line and just move it up. And of course, it's rescaled the axis, but now you can see that the mean is 3, and it's going up to 6, down to 0 and up to 6. We can change the mean to be what we like. There you go. So from 39, it's going from 36 to 42. But we can also change the variance as well. Let's go back to mean equals 0. Standard deviation equals, let's say, 5. Well, let's go back to 1. So that's the standard QQ plot. If I change the standard deviation to, let's say, 10, we can see that the mean is the same, but instead of plus or minus 1, it's plus or minus 10, you see, because it's going up to 30 and down to minus 30. And if I give it a tiny standard deviation, you can see we can play with the distributions. Gives a straight line. The line is straight, whatever value of mu and sigma squared we use. which is a pleasing feature. Again, you don't normally get that with other distributions, the badly behaved ones that I've alluded to. You don't have this nice functionality where you can plot things on any axis at all in a straight line. It turns out, and it's kind of obvious when you think about it, but I don't want to labour the point, that if we fit a straight line to our points, then the intercept equals the mean, and the gradient equals the is it the standard deviation or the variance? I think it's the standard deviation. I always get confused. A monkey would remember it right half the time, and I get it wrong. So let's just have a look at this. Let's just do standard deviation equals 3, mean equals, let's say, -4, AB line 4, 3. You see, this is where I'm not sure. Is it the standard deviation that's the slope or the variance? I can never remember. Let's just try the standard deviation. Oh, -4. You see what's wrong? That it went through +4, and it should have been -4 because I typed it -4 here. So I got a -4 there, and should have been a minus. Can't even. Oh, you can. So it is the standard deviation. There's a couple of other techniques where it is the variance, and I tend to get myself tangled up. So let's go back to a real example. Now we know how it behaves. We can go trees volume. We'll call it X.
Can I ask you a
Go for it.
about the ppnorm? So for your first one, it looks to me like the y-intercept is at about -6, -7. I'm not knowing how.
The question was, that's an excellent question. I want people to ask this question. The question was, the intercept for this one looks like to be -12 or something. That's what you're asking, isn't it? Yeah. But it's the intercept at x equals 0, which is this one. Yeah? Excellent. That's what I want to see. People are looking at that, weighing up what I'm doing and saying, does it make sense? Is it consistent? Does the world make sense? If you do that for everything, you realise this kind of thing, and you can construct the reality, because next time you see it, you'll think, oh, that was that bit where I asked the question and it was the wrong way because it was a 0. Yeah? And you've constructed that. I want you all to do this. I want you all to do it as a habit. I want you all to challenge it. If I'm saying something, I could just have got it wrong. Well, I did get it wrong the first time, but I could just be bullshitting you, or getting it wrong, or getting confused. If you see a mismatch in what I'm saying and what I'm doing, you put your hand up and say.
So it looks like actually what he was looking at was, it looks like is a -7.
Yes.
On your y-axis, if you were to come straight over to your.
What we want is that I'll put it on.
Come over to -1 instead of 0.
So we're looking here, yeah, at -4, and I put it at +4 by mistake. That's what you're saying, isn't it? There's my trees data set. Just make it more visible. Is that straight or not? Remember, it's not exactly straight. Looks a bit wibbly wobbly to me. Let's have a look at how straight real data is. Oops. 31. So if I go qqnorm, R norm of 31, what we'll get is an idea of how this behaves with truly random data, and we'll get a feeling for how the randomness of the Gaussian sampling process affects the... they all look quite straight to me. See, I'm doing it again and again to get myself an idea of the variability. Reasonably straight. Let's go back to my trees. It's within bounds of possibility, isn't it? Try a log transform. It's not that much better, is it? Oh, I did it repeatedly. But of course, it's the same because there's no randomness in there. What I'm going to do now is give you a couple of ways. What time is it? I'm going to give you a couple of ways to get p-values for your hypotheses. Let's have a look at this. I've got two values, x and y. There's my empirical cumulative distribution function of x, and I think I can do this. Yeah. So I'm just using random data, but your data will be the data from your portfolios. It'll be proportion of questions that you get right. It'll be the size of your fish. It'll be the, I don't know. Now, as it turns out here, these two data points, these two data sets, x and y, were drawn from the same distribution, both are standard Gaussian. But of course, the empirical cumulative distribution function doesn't lie on top of, they don't lie on top of each other because there's crud everywhere. Random. And if you take that as a model for your data sets in your portfolios, you will have this nice feature of randomness. What we need is an objective way to compare two ECDFs. Which one do I rub out? This one? Or that one? Does it matter? Okay. We need to assess data sets are drawn from the same we need a way to measure how far apart these two are. And I talked about this yesterday. What we do is we find the maximum difference. You see they're quite close here, but they're far apart there. It's there, isn't it? That's the biggest difference between the two. You see they're quite close here, maybe here. Maybe it is there after all. It's a bit hit and miss, really. We find the point, the position of maximal deviation between the two. This is D. And it turns out that D has a specific distribution called a Kolmogorov distribution. No. It's got a specific distribution called the Kolmogorov distribution if x and y have the same distribution. Which equals R null. I don't want to go into the details of it. But it should be clear to you that however I distort this x and y axis here, if I squash this and stretch this bit and squash it, or apply some weird logarithmic transformation, that D doesn't change. Yeah? Because it's a maximum. Wherever it is, its position might move about. If I square this axis here, or take a logarithm, or dick around with it, the position of this maximal deviation will move about, but the value of it won't. So D is what you say invariant. D is invariant to transformations. So specifically, D does not care what the distribution of x and y is, only that they are the same. Compare the null hypothesis of the t-test, which is that the mean of x equals the mean of y, but you don't care where. So in the t-test, you're asserting, the null hypothesis asserts that the mean of x equals the mean of y, but we don't care where. It's just somewhere, but we don't know what they are, they're equal. This is a more sort of general way of looking at it. The null of this distribution here doesn't care what the distribution is. It could be normal, could be Gaussian, could be a beta distribution, could be anything. It doesn't matter so long as they're both the same. You're testing for two distributions having two data sets, x and y, having the same distribution. But what that distribution is, you do not know, and as far as this test is concerned, you do not care. You can subsume all of that, all of this complicated calculation, which is to work out D, fit a null distribution to it, null hypothesis. Where's this thing from? This thing is from this Kolmogorov distribution, which I won't go into. Here's our observed value of D. P-value. We're getting the same argument again. We know what D looks like under the null hypothesis. It looks like this Kolmogorov distribution, which I could give you. I could give you the maths if you wanted. Work out the p-value. So let's have a look at that. How do we do it in R? That's it. ks.test x, y goes through this whole process, calculates the empirical cumulative distribution function, finds the biggest difference, calculates this thing here, this distribution D, this Kolmogorov distribution, which is the distribution irrespective of the distribution of x and y, just so long as they're the same, and calculates the p-value all in one line. Bang. Significant or not? No. No, no. Eventually I'll get a no. Yeah, eventually I'll get a type 1 error. Well, you get the idea. Okay. If I vandalize the null hypothesis so that it's not true, the mean is different, I will now get a significant p-value. It's picked that up. It's not a sensitive test, it's got low power. I'll write that down. KS test. You'll remember what power is because I've been banging on about it. Compared with the t-test. But it's very general.
So that first one, before you did the mean of x,
Yep.
6, your D is 0.4. The difference is 4.
This one?
Yeah.
Oh, yes, the D, that's the difference.
Yeah.
And here it's 1. So the
Difference of out of what? Out of
1, it can, well, it's because it's the difference between two cumulative distribution functions, yeah?
Yeah.
So there's 1, and if I draw another one in a different colour,
Right.
Looks like that, yeah? It's here, isn't it?
Right, okay.
So it can't be bigger than 1 because each curve is bound above by 1 and below by 0. So it's sort of out of 1. This is another reason why it's quite clever, because it's taken the units of the observation out.
The 0.4, the difference 0.4 is
The maximum difference.
maximum.
That's the maximum difference.
Yeah, so, but,
Yeah, it's just constructed two cumulative distribution functions and cruised along and found the biggest difference. So it can't be bigger than 1, and it can't be smaller than 0, I guess, because it's a difference. And you'll see it's a two-sided test as well, so we can muck around with one-sided and two-sided values if you're really desperate. I think that's a good place to have a break. I'm going to have a break for 10 minutes, and then I'll come back, because I've got Wilcoxon test and confidence intervals to talk about after the break.